In this example, we're given a circuit that contains a single storage element, and that's this capacitor in here. So it's a first order circuit, and since the voltage source that we have is DC, and this is a dependent source, so it's a first order transient circuit. Okay, and what happens in here is we have a switch, and that's what creates a transient state. That switch has been closed for a very long time. That's what we're being told. And at time t equals 0, we just basically open it. By opening it, we're just introducing that 6 kilo ohms in here. So before the switch, basically before time t0, that switch is closed. That means the current is actually bypassing the 6 kilo ohms, so as if this 6 kilo ohm does not exist. And after the switch is basically opened, that 6 kilo ohms is part of that circuit. And what we're being asked to compute is the I naught going through this particular 4 kilo ohm, okay, for t is greater than 0. That's what we're being asked to compute. Of course, we can write differential equations and solve these differential equations to describe this RC circuit. However, since it's a transient circuit that has just DC sources in here, we should be able to use the general solution to find it. And the general solution tells me you have to find the initial, the final, and the tau, and we should be able to solve everything in it. So what I will be doing is, in addition to finding I naught of t, I will also find the VC of t. You can spend some time on it and thinking if you could relate VC of t in terms of I of t. You probably will be able to come up with an equation that does that, but I'll just basically compute them differently. So this example will utilize a lot of circuit analysis techniques, so I recommend that you do it on your own before looking at my solution. Okay, so what I will do right now is I'll just basically go and get started with the initial condition. So I'll basically, let's find the initial condition, okay? Okay, so by finding the initial condition, let me just redraw that circuit. Initial condition, we usually utilize the circuit right before switching. Okay, so what we will say is, well, right before switching, what happens? Well, what we have is the 6 kilo ohm is not part of the circuit. We just basically eliminate it because it's shorted out. Okay, and also similarly, you'll see that this particular capacitor in here is also an open circuit because this is how we deal with those. So what we have in here, plus minus VC, and I'll call it 0, 0 minus. So this one here is a T0 minus right before switching. So the switch has been closed for a very long time, and right before we switch, this is what happens. And just to be consistent, this will be I0 at 0 minus. This isn't the initial condition that we're looking for in terms of the current. What we're looking for is typically 0 plus, but I'll just compute it anyway. VC of 0 minus, plus, or 0 are the same because of capacitor opposes the change in voltage. All right, so we have the circuit now, and what we need to do is we need to find those two in here. So there's multiple ways we can do it, nodal, mesh, whatever you want to do. I believe that mesh in this particular case will be the simplest, because if you just call this your I of A, which is this current in here, okay, and if you call this one here is I of B, you will realize basically you have to write just a single mesh here, because this one here is the same as a current source. And this current source, by the way, it depends on I of A, which is one of these here. So let me just write mesh. So what we're going to do is mesh at I of B, okay, I use lowercase, so I of B. So what we have is the following. We have I of B is just simply negative 2 I of A. So this is the first of two equations that we need to write. Now the next equation is mesh at I of A. So what we have is we have negative 12 plus 6 I of A and plus 4 I of A minus I of B equals 0. So what we have in here is two equations, two unknowns. You can clean them. Let me just highlight them in here. You can just basically do the algebra just to solve them to figure out what the I of A and I of B is. So what you'll end up with is I of A will be 2/3 of a milliamp, and I of B in this particular case will be negative 4 divided by 3 milliamp. But not I of A and I of B is not what I'm looking for. What I'm looking for is actually this current in here and this VC. So let's figure out what this current in here. This current is simply going downwards, so it's in the same direction as I of A, opposite direction of I of B. So what we have is I0 not in here will be just simply I of A minus I of B, which is 2 divided by 3 minus 4 divided by 3. That's 6 divided by 3, which is 2 milliamps. Right, so let me just rewrite this one here. I naught 0 minus here is just simply 2 milliamp. So it's right before switching. That's what we have in here. So I'm going to just highlight this in red. Now we'll figure out one of the two things I'm looking for. What we need to do as well is to figure out that, and there's multiple ways to do it, but I believe a simple KVL equation across the outer loop in here should do. So you can just basically say KVL. Okay, let me just remove these highlights so that we don't have to refer to them anymore. Okay, so this KVL will tell me negative 12 plus 6i of A, I believe, plus 6i of B. Okay, and then the 3 in here. So what I've done is, this is the negative 12, this is 6i of A, this is 6i of B. 3, well, this 3 has a voltage drop of 0 because there's no current flowing through it, plus VC of 0. Okay, and that equals 0. We know the value of I of A. We have figured this out in here. We just substitute. We know the value of I of B. We just substituted this in here, and we should be able to tell what the initial voltage across that capacitor is, and that value should be 16 volts. That's what we have. All right, let me just highlight it. So we're not quite done with the initial condition, because, well, again, what we're looking for in terms of the current is actually we're looking for I not at 0 plus. So what I will do is I'll just continue looking at the initial conditions. Okay, but now I'm going to target the other I naught. So this here is not really usable. Okay, but I just computed it just so that you can see that effect. All right, so let's continue. What we will do is I'll just take a look at this circuit right at, I will tell you this is exactly when we open the switch, so 0 plus. By opening the switch, what we have is the following. We have this particular here will be basically gone. I introduced a 6 kilo ohm at this point. Okay, so let me just do that. And the capacitor in here, while it's still a capacitor, what we really care about is the following. At the point, because it opposes the change in current, what we have, or the change in voltage, what we really have in here is actually plus minus VC0, which I know it's actually 16 volts because we just computed it. So what I know is actually between here and here I have 16 volts. That's what I know. All right, do I know anything else? Well, do I know this current in here? This current in here? No, I do not know it. I know right before the switching, not right after the switches, and it's not the same. And that's what we're after at this particular stage in here. So we continue, and what I will do is I'll say basically at finding the initial condition, finding initial condition at t equals 0 plus. That's what we're looking for. Okay, so again, there's multiple ways that we can do this, and what I will do is I'll refer to mesh. Since I'm looking for current, I'm just going to be using mesh current. So what I'll have is I'll have this one here. We're going to call it IA. This is different than the IA and IB that we've done before. You can call it IA prime if you prefer. I'll just basically deal with it as if it's a new circuit. This one here is IB, and we can technically write in here as I of C. Okay, actually we will have currents because this voltage in here is actually 16 volts. So now, and this voltage here is not 16 volts. So there will be some current in here. So the mesh current here is warranted in this particular case because we have a 16 volts, and that 16 volt will actually move things around. All right, so we write 3 mesh equations. Of course, I could have easily written 2 null equations, for example, one in here, one in here as well, whichever you prefer. But if you think about it, these 2 here is a super mesh. So at the end of the day, I'll end up writing a couple of equations anyway. All right, so let's do mesh at I of A, and what I'll end up with is negative 12 plus 6 I of A plus 6 I of A plus 4 I of A minus I of B, and that should be equal to 0. Basically, I wrote this particular mesh. So now what we do is you can do the algebra, and what you'll end up with is the following. You'll end up with 16 I of A minus 4 I of B equals 12. Okay, let me just highlight this so you can see it. This is the first equation out of 3 because I have IA, IB, IC. All right, so we continue. What we do is we do the super mesh. So at the super mesh, what we have is the following. The super mesh is here. Okay, so that's what we do. We have a 4IB minus IA plus 6IB plus 3IC And what do we do to this here? Well, all we have to do is just incorporate it. It's a voltage already. Remember, what we're doing is we at super mesh we're writing KVL. So this one here is just simply plus VC0, which I know is actually 16 volts. I know that this is here is just 16 volts, so I can just substitute it, or I'm just going to write it for the sake of clarity, and that will be 0. So what we do is we rewrite this algebra, and what we'll end up with is -4 I of A plus 10 I of B plus 3 I of C equals -16. So that's the second equation out of 3. Okay, so the last equation we can get it from the constraint. Okay, so the constraint that is imposed by this dependent current source. So what this constraint tells me that 2 I of A is simply I of C minus I of B. That's what this tells me. And with the algebra that we've been doing, and we'll end up with 2I of A plus I of B minus I of C equals 0. So that's the third equation. So you take a look at these three equations, three unknowns. What you'll end up with is the following. You'll end up with I of A for this particular case will be 23 divided by 54 milliamps. And the I of B will be -35 divided by 27 milliamps. And then the I of C is -4 divided by 9 milliamp. So what are we looking for? Well, actually we're looking for this current in here, which relates to I of B and I of A. So let me write this equation for it. So I naught of 0 plus, right after switching, it is simply I of A minus I of B, which is 23 divided by 54 minus, which is plus 35 divided by 27, which actually is 31 divided by 18 milliamp. So let me rewrite this here. So what I have is, in terms of initial condition, 0 plus is 31 divided by 18 milliamp. So we highlight it since we don't need these anymore. Okay, so we highlight this here in red, and that's basically the initial condition I'm looking for. So as you can see, so we started with 2 milliamp, and now it's not 2 milliamp anymore, it's something else, and that's okay. But the VC before and right after is the same, and we typically use it right before switching to compute such a VC, or maybe I of L, and right after switching, like at T0 plus, we utilize this value to compute the value that we're after. And now we move into finding the final values. So what we do is we need to find finding the final values. Okay. So let me just redraw the circuit in here. So this is the circuit that we have, and what we have is the following. The switch has been opened, so now the 6 kilo ohm is part of the circuit, and if we wait for a very long time, this also will be open source or open circuit. So this becomes in here plus minus VC final, and this one here will be simply I not final. That's what we're after. So we're after these two values in here. All right, and again, multiple ways that we can do it. I think probably mesh. We can do nodal if you wanted to. It's up to you. I'll just do mesh for now. Okay, and I'm doing mesh because I'm looking for this particular current in here. Okay, so mesh will do, for example, here I'll have I of A, and then here I'll have I of B. Let me just rewrite this. This is how it looks like. It's the same. It's just so that it looks the same. All right, so what we're going to do is we're going to do mesh at I of A, for example. Actually, let's start with, well, we'll start with I of A, that's fine. So at I of A, we're going to be doing -12 plus 6 I of A plus 6 I of A plus 4 I of A minus I of B equals 0. Okay, and you can of course do the algebra to figure out what this means in here, and you'll solve it. But what I'll do is I'll skip ahead and I'll just tell you, well, also what we can do is mesh at IB. Actually, we're not going to be writing mesh at IB. There's no mesh in here because simply IB is just equals to the -2IA. So what we have in here is we have one equation with two equations with two unknowns. We should be able to solve them to figure out the following. We'll end up with simply I of A will be 0.5 milliamp, and then I of B will be -1 milliamp. All right, and what we're after, we'll be using these to figure out the I naught F is just simply I of A minus I of B, which is just simply 0.5 minus minus, which is +1, which is 1.5 milliamp. And that's basically one of the final values. This is the final value of the current that I'm looking for, 1.5. Now, again, I'm looking also for this final value in here. So there's, again, multiple ways to do that. What I will do is I'll just basically use a KVL equation across this loop in here. So this KVL will tell me the following. It's -12 plus 6I of A plus 6I of A plus 6I of B plus, well, 3 doesn't need anything because this is 0, because if we wait for a very long time, this is here, it's an open circuit, so there's no current flowing through this, so this doesn't exist. And then that tells me VC final equals 0. And of course, we know the value of I of A, and we can substitute in here. We know the value of I of B, we can substitute it in here, and we'll end up with the following, which is the VC final is just simply 12 volts. That's what we have. All right, so we figured out the initial condition, we figured out the final conditions. So what's left? Well, what's left is the time constraint. Okay, so let's find the time constant. Okay, so we'll put the circuit once more in here just to see it. Okay, so what we have is the following. So we do this here, we do this here, we open that switch, and at the time constant, basically, we're going to see it in here. All right, so what do we have in here? So what we have is, what we're looking for is typically the R Thevenin seen from here. So I need to find the R Thevenin from here. And since I have a circuit that has a dependent source, that means I can't turn off the resistors, or I cannot turn off the sources and just figure out the combinations of the resistors. So what I need to do is I need to use the second or third method. The second method basically tells me let's figure out the I short circuit, or the third method, let's connect some sort of a test source in here and figure out the V if it's a current source, or I if it's a voltage source. But what I do know is the following. I know the open circuit, which is the V Thevenin. And the reason why I know it, because this is actually the same VCF. It's actually the same thing, and I can write it in here. So the V open circuit, which is the same as the V Thevenin, is the same as V capacitor final, because this is what the capacitor does. It becomes an open circuit in here anyway. So I know what the open circuit after switching, which is just simply 12 volts. That's the V Thevenin. So I'm not after the V Thevenin, but the reason why I'm writing it is because I'll be using the fact that R Thevenin is just simply V open circuit divided by I short circuit. So what I'll be doing is I'll actually take a look in here and just tell you, let's figure out what this I short circuit in here is. Once we know, we just substitute it, and we will be able to figure out what the R Thevenin is, and we can compute the tau, okay, the time constant. And of course, tau in here, it's an RC circuit, so it's just simply R times C. That's what it is. All right, so how do we find the I short circuit? Well, again, nodal or mesh. Since I'm looking for a current, I'll just use nodal. This is I of A, this is I of B, this is I of, well, I'm going to just call it I short circuit because this is exactly what I'm looking for. Again, these I of A, I of B, and I short circuit are not the same here, are not the same in here, and so forth. They're not the same. They're different currents in here. I'm just keeping the naming just so that we don't get confused. All right. So what we need to do is we need to do right mesh at I of A, for example. That will give me -12 plus 6 I of A plus 6 I of A plus 4 I of A minus I of B equals 0. And then at mesh, I believe what we do need is actually a super mesh in here, okay? So that's not a mesh equation anymore, that's a super mesh, okay? So at super mesh, what we'll end up with is the following: 4 I of B minus I of A plus 6 I of B plus 3 I short circuit equal 0. I believe I captured all of them, 1, 2, 3, 4. Yes. So let me just highlight the equations we're getting. We're getting this equation in here, in this equation here. So I have three unknowns. I need another equation. That equation will come from the constraint. Okay, so three unknowns, three equations. So the constraint tells me that 2I of A, which is the current source, is just simply I short circuit minus I of B. So that's basically the last equation. So three equations, three unknown. We should be able to solve them, and what we'll end up with the following. I of A is just simply 13 divided by 18 milliamp. I of B will be -1 divided by 9 milliamp. And then I short circuit, the one I'm after, is 4 divided by 3 milliamp. So of course now I know my I short circuit. Okay, since I know my I short circuit, our Thevenin is just simply V open circuit, which we decided that it's 12 volts divided by 4 divided by 3, and that should be equal to 9 kilo ohms. Okay, so that means tau is just simply R Thevenin times C, which is 9 times 10 to the power 3, and the capacitor is, I believe it's 100 microfarads. It is 100 microfarads. It's here. So we have to just write times 100 microfarads and times 100 times 10 to the -6, and what we'll end up with is 0.9 seconds. Okay, so that's basically tau. So let me just write it. Tau equals 0.9 seconds. All right. So we have that now here. I think we have everything we need. So let me just summarize them here. So I went ahead and I copied all these summaries in here and all the final and initial values and everything we found. So what we have found in terms of the I naught, we have found right before switching that the I naught was 2 milliamp, and right after switching we figured out that 31 divided by 18 milliamp. And if you wait for a very long time with the switch open, it will become 1.5 milliamp. And similarly, we found the initial voltage across this capacitor is just 16 volts right before switching and right after switching. There's no change in there. And if we wait for a very long time, that becomes 12 volts. We also found the time constant to be 0.9 seconds. So now we have everything we need to actually compute or write equations. So if I'm after I naught of t, all I have to do is just basically say, okay, what we have is, according to that, it should be I naught final plus I naught evaluated at 0 plus minus I naught final e to the negative, well, t minus t0, which is just 0, divided by tau. Okay, so we just substitute. That will becomes I naught of t. It's just simply the final, which is 1.5 plus the 0 plus the 31 divided by 18 minus 1.5 e to the negative t divided by 0.9. And that will becomes I naught of t equals 1.5 plus 2 divided by 9 e to the negative t divided by 0.9, and that's milliamp. And that's exactly t is greater than 0. So that's what we have in here. That's what we're looking for. That's what we're being asked to compute. Okay, and you can substitute values just and sketch it and do whatever you want. You'll see that if t equals 0, the whole thing here is 1. It becomes 1.5 plus 2.9. When t equals infinity, that becomes basically 1.5. All right, so we can do the same type of things for the VC. Okay, it's just now we utilize these values in here. So what we can do, let me just write it in here. What we have is VC of t, the voltage across that capacitor in here, which is this one here, VC of t, is just simply the following. It will be VC final plus VC evaluated at 0 minus VC evaluated final e to the negative t divided by, well, tau happened to be 0.9, but we're just going to write it as tau. So VC of t is just simply VC of f, which is 12 plus 16 minus 12 e to the negative t divided by 0.9, and that becomes 12, I believe, plus 4 e to the negative t divided by 0.9, and that's volt, and that's for t is greater than or equal to 0. That's VC of t. So that here gives me the value for this particular voltage in here. Okay, that's this one here. And I'm equal to 0 in here because it opposes the change in voltage.